Welcome to Lesson 12A, Compressible Couette Flow Introduction. In this lesson, we'll briefly review the compressible forms of our differential equations of motion, and then I'll start a simple example problem of compressible flow, namely compressible couette flow. In this lesson, we'll discuss only qualitatively the shape of the velocity profile, which will be different for gases and liquids. By way of introduction, for incompressible flow, the continuity and Navier-Stokes equations are uncoupled from the energy equation. We assume that there was little change in temperature, and fluid properties like density and viscosity are constant everywhere. For compressible flow, however, all the fluid properties will depend on temperature. Therefore, continuity and Navier-Stokes equations are coupled with the energy equation. I'll mention briefly that we previously discussed the Boussinesq approximation, which was a kind of compressible flow in which we had very small changes of density with respect to temperature. In fact, we assumed that they were linear and we kept mu equal constant. But in the general case, these properties depend on T, and so we need T in the energy equation since it appears in the Navier-Stokes equation. Consider pretty much the simplest possible example, which is compressible couette flow. Here's the setup. We have two infinite flat plates aligned with the x-axis, separated by distance capital H, with the upper wall moving and the bottom wall stationary. We solved this problem previously for incompressible flow, and in that case we had a linear velocity profile where u of y is 0 at the stationary lower wall and increases linearly to capital UE at the upper wall. For the compressible case, we make some of the same approximations and assumptions as we did previously, but we allow mu and rho to be functions of temperature. Since these walls are infinite, there's nothing special about any particular x location, so we assume that all flow field variables and fluid properties are independent of x. The flow is steady and two-dimensional. These three approximations tell us that since del x of anything equal del t of anything equal del z of anything equals 0, all properties and flow variables are functions of y only, as I show here. Density, viscosity, pressure, component of velocity in the x direction, and temperature are all functions of y only. For the compressible case, u must again go from 0 to capital UE, but the profile is not expected to be linear because of these non-constant properties. Dude, why do you use E for the subscript for the upper wall instead of like U for upper or T for top or something like that, man? Good observation, Joe. It's because when we get into boundary layers, which is our next topic actually, we sometimes use E as the edge of the boundary layer. And since the equations are pretty similar, we used subscript E up here for the top plate as well. Oh, thanks, dude. That makes sense now. Now let's simplify our equations as much as possible. Keep in mind that we must use the compressible form of our equations from a previous lesson. Continuity is del rho del t plus del x of rho u plus del y of rho v plus del z of rho w equals 0. But the flow is steady, our assumption 2. Del x of anything is 0 by assumption 1. V is 0 by assumption 4, and del z of anything is 0 by assumption 3, so continuity reduces to 0 equals 0. In other words, continuity is exactly satisfied for this problem. Now consider the x momentum equation, where we must again use the general compressible form. Recall the Cauchy equation, rho dui dt equal rho gi plus del xj of tij, where tij is our stress tensor. And for a compressible Newtonian fluid, we had written out previously that tij equal negative p delta ij plus mu del ui del xj plus del uj del xi plus lambda del del xm delta ij, where recall this lambda is the second coefficient of viscosity. Well, let's plug this into here to write out the compressible Navier-Stokes equation, and we'll consider only the I equal 1 component, or the x component. I'll expand this out here, and the first term on the right-hand side goes away by our assumption 5, which is that we neglect gravity. Let's expand this term. Now let's cross terms off that are zero according to our approximations and assumptions. The flow is steady, u is not a function of x, v is 0, the flow is 2d, p is a function of at most y. Again, number 1 gets rid of del u del x, and here as well. V is 0, therefore del v del y must also be 0, and again the flow is 2d. Because the flow is 2d, the last term goes away, and again v is 0. So the only thing left is this one term from our compressible Navier-Stokes equation. Notice that lambda dropped out even though this is a compressible flow. The bottom line then is del del y of mu del u del y must equal 0, where we must be careful to keep mu inside the derivative since it does vary with y. But we can change these to total derivatives since both mu and u are functions of y only. This is the final form of our Navier-Stokes equation, which we can easily integrate, giving us mu du dy equal constant. Recall, when we did the incompressible form of this problem, we defined the 2D shear stress as tau, which is the shear stress parallel to the x-axis on the bottom of a fluid element, which we previously defined as tau 2,1. So it turns out that even in compressible Couette flow, if we define tau the same way, mu du dy, it's still a constant. I'll call this equation 1, which I'll rewrite here on the new page. And now let's do a qualitative analysis of our compressible Couette flow, in particular the velocity profile, u as a function of y. As we mentioned, in the incompressible case, the velocity profile is linear. In other words, the slope is constant, since mu is constant in this equation. But mu is not constant for the compressible case, so the velocity profile may look something like this or something like this. We'll still have the boundary conditions that u equals 0 at the lower wall and u equal ue at the upper wall, but our goal is to figure out what kind of profile shape we have when mu is not constant. For simplicity, we'll let mu be a function of temperature only, and we know that temperature is a function only of y, therefore mu is also a function of y only. Let's consider gases. For most gases, mu increases as temperature increases. So looking at our Couette flow, let's consider first the case where Tw, the temperature at the lower wall, is greater than Te, the temperature at the upper wall. In other words, this upper wall is cold and the lower wall is hot. Qualitatively, since mu goes up as temperature goes up, near the upper wall, mu is relatively small, therefore du dy must be relatively large. We expect the slope to be large. The opposite is true here. Since mu is relatively large at this higher temperature, du dy must be small. The slope must be smaller like that. Thus the velocity profile will look something like this, going from 0 at the lower wall to ue at the upper wall. In other words, it's concave compared to the incompressible case. If we have the opposite case, where Tw is less than Te instead of being greater than Te, we now have a cold lower wall and a hot upper wall. So everything's opposite in the sense that we expect a small du dy near the top, since mu is large, and a large du dy near the bottom, since mu is small. Thus our velocity profile will look something like this compared to the incompressible case. This profile shape is convex. Now consider liquids. For most liquids, mu has the opposite behavior, namely mu goes down as temperature goes up. So for liquids with Tw greater than Te, we expect a small slope near the top, which is cold, and a large slope near the bottom, which is hot. Thus the profile looks something like that, similar to our Te greater than Tw case for gases. In other words, we expect a convex velocity profile. And for the other case where Tw is less than Te, the slopes are opposite and we get a concave velocity profile. The bottom line is that the liquid profile shapes are opposite to those of gases. Again, this is just a qualitative result. To actually get the shape of these profiles, we need the energy equation to get temperature as a function of y, which will give us mu as a function of temperature or indirectly as a function of y. Since mu appears in the momentum equation, the energy equation will be coupled with our momentum equation. We'll add the energy equation to our analysis in the next lesson. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.
That's all there is to it.